Okay, so in this video, we will discuss matrices and polynomials. Now, we will be taking powers of a matrix, and so the matrix must be a square matrix. So let's consider a simple example. Take a polynomial, p of x, say x squared minus 3x plus 2, right? You could replace x by any kind of real number that you want. You could say, well, okay, well, p of 7 will be 7 squared minus 3 times 7 plus 2, which would give you 49, minus 21 plus 2. Negative 21 plus 2, negative 19. And the result would be simply 30. And this is just one example. You could replace x by any real number of your choice, and the result would be a real number. The question now is, could we perhaps evaluate the polynomial not at a real number of our choice, but at a square matrix of our choice? Can we make sense of this? Well, let's take a square matrix. For simplicity of the calculations, we'll take a 2 by 2 square matrix. Suppose we take the matrix 1, 2, 3, 4. Let's ask, can we make sense of p of a? Replacing x now by the square matrix A. Well, the only way to make sense of this would be to do a squared minus 3 times a plus 2. Let's see if we can make sense of this, or perhaps there's something subtle going on. A squared is a times a. 1, 2, 3, 4 times itself. Minus 3 times matrix A, so far no problem. Here's the problem, plus 2. As this stands, this is not defined. Here's a 2 by 2 matrix, here's a 2 by 2 matrix. Once we perform the subtraction, this will be a 2 by 2 matrix, plus a real number. We can't perform this operation. We can't add to a 2 by 2 matrix a single real number. What is here should also be a 2 by 2 matrix. How can we fix this problem? Well, if you think of it, we can be sneaky about this. If you go back here, you can view 2 as not just 2, but as 2 times 1. And you may ask, well, okay, once we jump from real numbers for x to matrices, well, what is the analog of the real number 1 in the realm of matrices? Well, there is a very special matrix that plays the role of the real number 1, and that is, of course, the identity matrix. So once we jump over matrices, 1 becomes I. And I will inherit the size of A. So because A here is 2 by 2, I will also be 2 by 2, therefore 1, 0, 0, 1. If A were a 3 by 3 matrix, I would now be the 3 by 3 identity matrix. And now this makes perfect sense. And we can compute this. Let's square A, so we'll have 1 plus 6, 7, 2 plus 8, 10, 3 plus 12, 15, 6 plus 16, 22. Minus, well, multiply every entry of the matrix by 3, so we get 3, 6, 9, 12, plus the matrix 2, 0, 0, 2. And let's see, 7 minus 3, 6. 7 minus 3, sorry, 4, plus 2, 6. 10 minus 6, 4, plus 0, 4. 15 minus 9, 6, plus 0, 6. 22 minus 12, 10, plus 2, 12. And there you have it. The polynomial x squared minus 3x plus 2 evaluated at the matrix A, 1, 2, 3, 4, gives the matrix 6, 4, 6, 12. And that's it. This is how you evaluate a polynomial at a given square matrix. The only subtle point is to replace a constant term as the constant term by 1 times 1, and then replacing 1 by the identity matrix. Let's look at one last short definition, that is the root of a polynomial. If you remember, the root of a polynomial is a 0. Well, we can make the same kind of definition for matrices. So we say that if you let A be a square matrix, and we have P of x being a polynomial, we say that A is a root of P of x if, of course, P of A equals 0. But we know P of A is a matrix, so of course P of A will equal the 0 matrix. So very simple and natural extension of the root of a polynomial when it comes to matrices. A real number of a polynomial would have a property of P of that real number being equal to the 0 real number. Well, a matrix is a root of a polynomial if P of A is the 0 matrix. Let's give a simple example of this. The matrix A, as we have used previously, 1, 2, 3, 4, is a root of P of x equals x squared minus 5x minus 2. Well, let's verify this. Let's evaluate P of A and see if we get the 0 matrix. Well, we'll have A squared, so 1, 2, 3, 4 times itself, minus 5 times A, minus 2, of course, 2 times 1, 1 becomes I, and let's see what we get. We have previously found A squared. If we just look back up, A squared was 7, 10, 15, 22. Minus the matrix 5, 10, 15, 20, minus the matrix 2, 0, 0, 2. And let's see if we get indeed the 0 matrix. 7 minus 5, 2 minus 2, 0. 10 minus 10, 0, minus 0, 0. 15 minus 15, 0, minus 0, 0. 22 minus 20, 2, minus 2, 0. And so our claim is correct. A is a root of this matrix, 1, 2, 3, 4, is a root of the quadratic polynomial x squared minus 5x minus 2, as P of A equals the 0 matrix. And that's it.